Hello everyone, welcome to this video. In this video, let's study about the next property which tell us that if the order we need to prove that when phi is given to be an isomorphism from some group G to the same group, right? In that case, if A is some element taken from the group G, then that element, the order of that element is equal to the order of the image of A, that is phi of A. So this thing we need to prove here. For the proof here, we assume that order of the element A is equal to n. Then because n is the order, so we have a to the power n is equal to e, such that n is the least positive integer of such kind. Now we assume that phi of A is equal to y. So what we need to prove? We need to prove that the order of this element y is also equal to n. For that, what we are doing, we are taking y to the power n and seeing what do we have. Y to the power n simply means phi of A raised to power n, right? And phi of A raised to power n, this thing is equal to phi of A raised to power n. Why? Because this is from our property 2. So phi of A raised to power n is equal to phi of A to the power n, and A to the power n, because we know it is identity, so it is phi of identity, and because we know phi maps identity to the identity, so therefore this thing is equal to the identity. Now this identity is same as this identity. Why? Because we are taking the same groups here, correct? So from here we obtain that y of n is nothing but identity. So this gives us that the order of y, which is nothing but the order of the element phi of A, this is less than equal to n, right? So why this? Because there may exist some integer m which is less than n, such that y to the power m is equal to e. So let's discuss this case. Is this case possible? If this case is possible, then we will say m is the order, otherwise n would become the order. So let's take this case when m is less than n and y of m is equal to identity. So in this case, we are writing this thing over here, right? And what is y raised to power m? It is phi of A raised to power m. Again, using the second property, we have phi of A to the power m here. So what we can do here next is we can pre-multiply both sides with phi inverse. Now because phi is 1 1 and on 2, so therefore its inverse would exist. So therefore we have phi inverse of E is equal to phi inverse of phi of A to the power m. So here in this case, phi inverse of E is just E according to the properties that we have already studied, right? And this phi inverse and phi cancels each other effect, so we are left with this element only, which is A to the power m. So from here we obtained A to the power m is equal to E. But this is not possible because we have assumed the order of A to be n. So n is the least positive integer such that A to the power n is equal to E. But in this case, we are having some m which is less than n and such that A to the power n is E. So this thing is not possible. So therefore, what do we have? This thing m less than n, strictly less than n, this is also not possible. M strictly less than n, this is not possible. So that means n becomes our least smallest positive integer such that phi y raised to power n is e. And what was y? Y was phi to the phi of A. So phi of A raised to power n, that becomes e. So the order of phi of A is equal to order of A, which is n. Right? So I hope you understood the proof of this property. Well, that is it for this video. Thank you for watching.